Good morning all. We'll continue our discussion on slope stability. Now, we have been discussing slope stability at least peripherally, starting off with the introductory part. Then we moved on to phi equal to 0 analysis. In between we had studied what are the forces which cause the slope instability and which are the forces which could probably resist the slope failure. We studied about the factor of safety. And now we'll try to discuss the second method included in the syllabus, which is called the Swedish circle method, to analyze the factor of safety of a slope. Now, quite like the previous example, I have a slope which is assumed to be a part of a circle or it's defined by an arc whose length is L. Now, this method, the Swedish circle method, is also called as the method of slices. Why? Because the fundamental principle here is to divide the slope into slices and then analyze each slice and then put everything together to get the factor of safety. Like I said, here the slip surface is assumed to be circular, which means it can be defined by a radius r and it can have a center O. And our slope is the same name, ADB, with an arc length of L. Now, this failure mass, ADB, is divided into slices using vertical lines, right? So now I can cut the vertical lines like this, and I'm dividing the entire mass ADB into slices. Now, I can take a single slide out of that and have a delta L length, and I can consider the equilibrium of that slice. Let's assume I'm taking this slice out of the wedge or the soil mass and analyze it for its equilibrium, which means I'm trying to analyze the forces which are acting on that slice, and I'm trying to get a factor of safety based on that single element. I have a single element here, which is a slice of ADB. Now, what I can do further is I can draw a normal to the curve of the slice I have taken, like this. And of course, the normal to the curve will pass through O, the center. Why? Because the normal to the curve is nothing but a radius, and that radius is tangential to the curve at any surface, right? So any surface will have a tangent and there'll be a line perpendicular to that tangent, and that will nothing but the radius. So that happens to be the normal to the curve. Now I can take that portion separately, quite like this. I have the slice here, I have the normal to the curve at this point, and through that point I can assume the weight of this slice to be acting downward. Now this weight will obviously be acting in the direction of gravity, what we call as a plumb line, right? So I have first force here, which is W, weight. I can have a second force here, which is a unit cohesion that will be acting in this direction. So this method being applicable to both type of soils, C-phi soils, I can have C here and I can have any other component phi, which we'll discuss further. So C is one component which will resist the slope instability, or when the slope tries to move downward and outward, C will try to resist it by acting upward. Now, since I've drawn a normal and the weight W is inclined to the normal, let's say at an angle alpha, W will have a component in the normal direction and in the tangential direction. In short, I can resolve W in the N direction and the T direction, the resultants of N and T giving me W. So I've written the angle alpha being made with the W and the normal. So weight W is inclined to the normal to the point at angle alpha with components N and T. Now there'll be a reaction R at this point which is again inclined to the normal. That reaction R is inclined to the normal because the soil is C-phi soil, which means friction exists. In short, the same principle of friction applies here. When you have a block kept on a surface, you will have a reaction and the mu R component will be at an angle. Quite the same principle applies here. So I have a reaction R inclined to the normal at an angle phi, which is the angle of friction, just as in case of frictional theory. So I can draw that here separately. The same slice, I have the normal, the same normal, I have the reaction R, which is at an angle phi with respect to the normal. Earlier, I had the weight W, which is at an angle alpha with respect to normal. So just think of one thing. These three things are acting on the same wedge. I have separately drawn for you to understand it better. So fundamentally, I have a slope ADB. I have taken the slice, one slice out of that, and I'm trying to analyze the forces acting on it. And from the resolved figure, I can write that N is equal to W cos alpha. From this figure, I can write N is equal to W into cos alpha. Likewise, I can write T equal to W into sin alpha. T is equal to W into sin alpha. The resolved forces. But from the reaction force R, I can write N as R into cos phi based on this figure, right? Now I have two equations for N here. Now I'm trying to take the moment with respect to O. Let's try to understand it again. The moment which causes a failure will be the component of weight, and the moment which tries to keep the slope in safety will be the cohesion and the friction. So the moment causing failure, MO, will be equal to T into R. T is the component of the weight in the direction tangential to the curve. So I can have T into R as the moment causing the failure. Now what is the moment resisting the failure? The moment resisting failure will have two components because it's C-phi soil. First component is the same thing as you have seen in the phi 0 analysis. That will be C into delta L into R. In the phi 0 analysis, we had studied that it is C into L into radius. Cohesion multiplied by the length of the arc multiplied by the radius. Now in this case I can write it as C into delta L into R because I've taken just a small slice whose length in this direction is delta L. Now that takes care of the C part or the cohesion part. Now coming to friction part, I can have R multiplied by R sin phi. Right, so R is a component of reaction which offers a lever arm of R sin phi with respect to O. So I can have the sum of the moments which resist the failure written as C delta L into R plus R sin phi. Now this factor is about clay cohesion. Now this part is about friction. Or, in short, I can rewrite it like this. I've rewritten the second term like this, and I can again rewrite it as N tan phi into R, because R sin phi is nothing but N tan phi from the previous slide. Now, since I know MR and MO, all I can do is just take the ratio. MR by MO will give you the factor of safety. Now that factor of safety will be for just this slice. So if you want to find out the entire slope's factor of safety, you just have to integrate, or you just have to find the sum, sigma function. When applied, will give you the factor of safety. So C delta L into R plus N tan phi into R by sigma TR. This thing will give the factor of safety for the entire slope from the basic slice, which I can write as CL plus sigma N tan phi by sigma T, while cutting the small letter r, the radius, from both the numerator and the denominator. So quite similar to what we have discussed in the phi 0 analysis, we don't stop the analysis here. What we have now is just the factor of safety of the slope ADB. Now we're not quite sure if that is the weakest plane. What we do is you consider another slope ADB dash or ADBB dash, etc. with a different geometry. Find the factor of safety. Likewise, you continue the analysis. So the slope geometry which gives you the least factor of safety will be the most prone failure plane.